So thank you very much, Angelica, for your nice introduction. Hello to everyone. I am very happy to be able to be with you, even with this screen separation. I am pleased to talk to you today about the use of technology and various uses of technology from the instrumental perspective. But I will start, as it was announced in the timeline, with a warm-up question. I don't know whether it can appear, so I will perhaps just tell you what I would invite you to think about. So I invite you to think about a situation in which you use digital mathematical technology, either as a teacher, if you are a teacher, or as a student during your PhD courses. So it might be a situation with a very usual way of using this technology. And the question that I would like to ask you is, how would you characterize the way of using technology? And so in order for you to focus on some particular aspects, you may think about what the technology is used for, what to do with this technology, who manipulates the technology, whether a teacher or a student, and what is the learner's cognitive activity during using this technology. So we will afford for 5 minutes in a group discussion about this question, and we will come back to this question after the talk. Thank you very much. So I hope you had some time, but not too much, to discuss about the question. So maybe you will, it will help you to give a sense to what I will present you about the different uses of digital technology. So I will follow this plan. So first I will start by a general introduction to digital technology, the role of digital technology, and I will introduce you two frameworks to think about its role. Then I will make a brief introduction to the theoretical concept that I will be referring to during my talk, which is mostly instrumental approach and semiotic potential of a tool. And then I will talk about these various uses of digital technology following one of the frameworks, and I will exemplify it on the dynamic geometry software. And I will try to provide some analysis of these uses from the instrumental perspective. So, about the role of technology in education, already in 1985, P brought to the fore two metaphors. The first metaphor is an amplifier metaphor, according to which technology changes how effectively we do traditional tasks, amplifying or extending our capabilities, with the assumption that these tasks stay fundamentally the same. On the other hand, there is a reorganizer metaphor that we can look at the role of technology, in which technology changes the tasks we do by reorganizing our mental functioning and not only by amplifying it. These metaphors echoes two approaches to e-assessment. This is a more recent work in which there are two approaches: migratory, according to which traditional paper-based tasks are translated into digital format but remain qualitatively unchanged. And on the other hand, there is a transformative approach to e-assessment, which aims at assessing skills and abilities that are usually not assessed. So from these two points of view, you can see that technology can be used just to amplify our capabilities, but not changing fundamentally the tasks that we do or how we accomplish them. And on the other hand, there is also the point of view that technology perhaps should change the tasks, or at least change the approach to dealing with these tasks, and to help us conceptualize differently our activities and our learning. So there are different frameworks that look at the role of technology in education, and one of those is RAD framework. You can recognize the replacement level, in which technology serves as just a different means to same instructional practices. There is, on the other edge, transformation. Technology invents new instruction, learning, or curricula. And in the middle, there is this amplification, what was already presented by P. Technology increases efficiency, effectiveness, and productivity, but of the same instructional practices. So the authors of this framework suggest using this framework to look at how instructional methods, how students' learning processes, and how curriculum goals are or not transformed or modified by using technology. Indeed, instructional methods can remain the same, but there might be some amplification on students' learning processes or transformation of curriculum goals. Another model, another framework that looks at the role of technology is the SAMR model. These four letters stand for substitution, augmentation, modification, and redefinition. So just to comment briefly about all these levels, on the substitution level, technology acts as a direct tool substitute, and it doesn't bring any contribution, any functional change. At the augmentation level, technology acts as a direct tool substitute with some functional improvement. At the modification level, technology allows for significant task redesign, and at the top redefinition level, technology allows for the creation of new tasks which are not conceivable without this technology. So you see that the bottom two levels enhance somehow instruction and students' activity, and at the top levels there is a transformation of the instructional practice and of students' approaches to mathematical learning. Just to give you an example, we can think of a mathematical quiz. So a teacher uses a paper-based quiz to ask some questions to students. At the substitution level, it will be just a translation of this paper-based quiz to a digital system, but for the student it will consist in the same way, checking the correct answer, and so there is no functional change from the student's point of view. At the augmentation level, we can think about the digital quiz, but with a functional improvement. For example, the system will provide feedback on the student's answer, whether it is wrong or correct answer. And so with this direct, immediate feedback, one can assume that the students will be engaged more deeply in the learning, because they will get immediate feedback, which will allow them to rethink the question that was not correctly answered. At the modification level, we can think about the quiz, for which the students receive correct or incorrect feedback, But in addition to this, the students might also receive some kind of indication how to remediate. So, for example, they might be encouraged to see one particular course or solve some particular activity according to the questions that were not successfully answered. And so at the last level, redefinition level, we can even consider a system that will provide each student with a personalized path through the questions according to the previous responses. So this definitely is very hard to imagine without technology. So I will now go further to present you a few theoretical concepts that I will be referring to when analyzing examples of use of dynamic geometry. So I will first introduce to you the instrumental approach, which is an anthropocentric approach to technical tools that complement purely technocentric approaches. In this anthropocentric approach, there is a consideration that the tools are here to respond to human needs. So the tools were made by humans to fulfill some specific needs. And so this approach hypothesizes that it is necessary to study relationships between humans and the tools, and so this relationship that is established between human beings who use these tools, and not only looking and studying the tools themselves. The instrumental approach is fundamentally based on the distinction between artifact and instrument. So an artifact is a material or a symbolic object which was firstly designed and produced by a person or a team of people so as to meet one or several precise goals. So it was actually designed for meeting some humans' needs. And so this artifact is still available for other people. The instrument, contrary to the artifact, is not given. The instrument needs to be constructed by the subject. And the construction of the instrument by the subject happens while using the artifact. So the instrument is a result from a use of the artifact. The subject builds the instrument from the artifact when using it during an activity to accomplish a particular task. So the instrument in the instrumental approach can be defined as the artifact or a part of it with the associated scheme of use. So I won't go into detail what a scheme of use is, but you can understand it as a particular way of using the instrument to accomplish a particular task. So I will try to exemplify this distinction. So here you see two artifacts, a compass and a cup of bottled milk. So you can imagine what one can do with those artifacts. With the compass, it is more or less obvious that you can draw circles, but you can also use the cup of bottled milk to draw circles. So this is something that kindergarten children do quite often. So we can consider a compass and this cup of bottled milk as the instruments for drawing circles. When we come back to the compass as the artifact, we can, on the one hand, imagine or transform it in a in an instrument for drawing circles, but we can also use it for marking of defined measured lengths. So from these examples, you can see that two different artifacts can be instruments for accomplishing the same task, and on the other hand, one particular artifact can become instruments, can give rise to two different instruments for accomplishing different tasks. The second concept that I will refer to during my talk is the semiotic potential of an artifact. And so Mariotti and Maracci define the semiotic potential of an artifact as a double relationship that can be established between the artifact and the personal meanings that emerge from the use of this artifact. They call this artifact signs. And the second relationship is between the artifact and the mathematical meanings that are evoked in the use of the artifact. And these mathematical meanings are called mathematical signs. So this is the schema that Mariotti and Maracci used to illustrate the semiotic potential of an artifact. So in the middle, you see a child, a student, using an artifact to accomplish a task. On the one hand, the student creates personal meanings, the artifact signs, from his or her activity with the artifact. And the aim of the activity is that the students can give mathematical meanings to this artifact sign. So evolve this artifact sign into the mathematical signs. And so very often this evolution is accompanied by teacher's mediation, so that the teacher helps the students to transform their personal meanings toward mathematical meanings. So back to my example of the compass and cap of the button of the milk bottle. If you look at the potential from this semiotic potential perspective, we can assign to the compass artifact signs in terms of the sharp tip that will be stable while drawing the circles. There is a rotating pencil tip, which is another artifact sign. And there is also another artifact sign, which is the gap between the compass arms that remains constant while rotating the pencil tip around the sharp tip. So these artifact signs can be transformed into mathematical signs in terms of a center of a circle. And so this constant gap evokes the mathematical property of a circle, which is the equidistance of points from the center. When we look at this very simple artifact, which is this cap, we can also look at the artifact signs. We can observe its round shape, and we can also observe when we try to roll it that it is rolling smoothly. So this might evoke the mathematical sign, which is the regular curvature. And so you can see that when drawing circles with this cap, there is no way of thinking about the center and equidistance of points from the center. So these two artifacts have a very different semiotic potential. So I hope these terms are clear to everyone. So I will now go to the presentation of these various uses of digital technology. And I will start by recalling Laborde work. In 2001, she already identified 4 different roles of dynamic geometry. One of these roles is mostly to facilitate material aspects of the task while not changing it conceptually. So this is almost a quotation from Laborde. And so, as example, she evokes drawing a figure with dynamic geometry tools. The second role is dynamic geometry to facilitate the mathematical task that is considered as unchanged. So she said that this is the case where dynamic geometry is used as a visual amplifier in the task of identifying properties. So you can imagine, for example, a polygon and its translated image, and the student is asked to conjecture relations between their sides. And so while dragging the vertices of a polygon, the translated image changes, and so visually the student can conjecture the properties that are unchanged while dragging. The third role is to enable to modify solving strategies of the task due to the use of some of the tools of dynamic geometry and to the possibility that the task might be rendered more difficult. So Laborde gives an example of constructing a square with a given side. And the last role is using dynamic geometry for solving tasks that only exist in dynamic geometry environment. And so here she gives an example of reconstructing a dynamic diagram. So if you look at these 4 different roles, and if you remember the SAMR model that I presented a while ago, you can perhaps make a parallel between the first role and the substitution level, the second one and the augmentation level, the third one as the modification level, and the fourth one, the redefinition level. So this observation led me to think about different kinds of possibilities of using dynamic geometry at these 4 levels and to analyze what they can bring and how they can contribute to the learning of mathematics and in particular geometry. So let me start by showing you a substitution level, a type of task that can be used with dynamic geometry at the substitution level. So Colette Laborde already mentioned free drawing. So definitely we can use this for just drawing any figure, any drawing with dynamic geometry tools. So this would mean that we just change traditional geometry instruments with the tools provided by dynamic geometry. So we can look at the semiotic potential of the traditional tools and the semiotic potential of dynamic geometry tools. So just a very simple tool, such as a ruler, to draw a line, and how we can draw a line with dynamic geometry. So you know that to create a line with dynamic geometry, you have to click on 2 different spots on the screen that will create 2 distinct points. And so if we look at the semiotic potential, we can observe that when you draw a line with a ruler, you don't need to materialize these 2 points, And so the mathematical meaning that is conveyed is the straightness. You draw a straight line, while the dynamic geometry tool conveys the idea that a straight line passes through two distinct points. This is even more visible with using compass. So the traditional compass, and with dynamic geometry, you have three different tools for constructing, for drawing circles. So I have the invitation to come back to the previous slide. Okay, so I will move to the example of a circle. So, as I mentioned, you have three different tools for drawing circles with dynamic geometry. And so there is one which is particularly interesting. It is the one that allows to construct, to draw a circle passing through three distinct points. So here again, we see that the semiotic potential is very different comparing to the traditional compass. And for example, this particular dynamic geometry tool, which conveys the idea that three non-aligned points define a circle. So this consideration, this observation, lead me to tell that even at the substitution level, where the students draw freely some drawings without paying attention to any geometric relations, might be a quite rich activity to discuss the differences between using the different tools, and to discuss the differences in the semiotic potential of the use of the tools. Unfortunately, this is very rarely done by the teachers who almost never take opportunity to compare tools of dynamic geometry and to compare them with the traditional tools. Instead, you can find resources that are proposed at the substitution level, while they might have been proposed with some more efficient exploitation of dynamic geometry potentialities. So here is an example. This is an example of a resource in which the study is focusing on the area of a triangle. So I will try to show you how this activity is expected to be done. So first, the student should construct a triangle and then create three distinct instances of other triangles and so on. So this is the activity. So the students start by constructing the triangle ABC. Then he or she should construct the line which is parallel to the base BC passing through A, and then the student is asked to place three distinct points, A1, A2, A3, and construct three different instances of a triangle and measure the area. And the observation that the student is supposed to do is that the area of all these four triangles remain the same. And so here one can wonder why the three instances are needed when one instance would be enough, and one can generate those different triangles and observe that the area remains the same. So I will come back to my slides. And so, well, this was an example of an activity that might be done at a higher level than just the substitution level. So let me now move to the augmentation level. At the augmentation level, there are very typical and frequently proposed tasks like conjecture or verify a geometric property, like this one. So here, maybe to go quickly, I won't switch to GeoGebra, but you can easily figure out what is the task about. So here you have a figure, a configuration, and a student is asked to move around the point M, which is bound to the circle, and to observe that the angle remains 90 degrees. So here definitely the drag mode is used, and its semiotic potential is explored. Indeed, the drag mode allows to generate a number of different configurations, so the student can easily identify the geometric property of the figure because it is the property that remains unchanged while the student is dragging the 3 points. So here, dynamic geometry plays a role of a visual amplifier and facilitates the identification of geometric properties. So you can see the difference between substitution, in which you don't move anything, with this augmentation level, in which dynamic geometry brings already a functional change. These kind of tasks are very common, and they are very frequently found in French textbooks. So here are just 2 examples taken from 2 different textbooks. They usually start by asking the student to construct a figure which will be a robust figure. That means that all properties will be maintained while dragging. And the last question prompts the students to drag some particular points and to observe something. So in this type of tasks, you will always find this kind of progress, very guided construction, and then prompting to drag and to describe observations. I will now move to modification. So this is the first level at the upper part of the model. And so here there is, for example, a task of constructing a robust figure. So the figure that must resist while dragging. So Laborde already gave an example of constructing a square from its side. So I will again share with you the dynamic figure. So here you should see 2 figures that seem to be squares. So one is built from the side AB, and the other is built from its diagonal EF. So the idea, we can check whether the student actually succeeded the construction. So by dragging the 3 points. So here it seems to be a correct construction, so the square remains a square. If we want to be sure, we can display the measures and so on. So this figure seems to be a square. What about the other? So here again, we can try to drag to verify, to validate or invalidate the construction. So we can drag the point A, and so we can observe that it seems to be a square. We can drag another point. It seems to be a square. There is another 3 point, and so when we drag the third point, we actually figure out that it is not a square. The drag mode can be used here to validate or invalidate constructions. So back to my slides. In this kind of task, the role of dynamic geometry is very particular because it forces the student to resort to geometric properties in order to construct a robust figure. So this is very different comparing to a construction on paper and pencil in which the student can control the construction by perception and not necessarily resort to geometric properties. So this is something which is valued by the teachers. And so the drag mode here is used to validate or invalidate the construction. And so a contribution to learning geometry is that this kind of tasks can facilitate distinguishing between drawing and a figure. That means between the actual trace of a figure on a paper or on a computer screen and the theoretical concept, which is the figure defined by geometric properties. I would like to show you another example of a task which is at the modification level, which is searching for conditions that lead to obtaining a specific configuration. And so this kind of construction is called soft construction. So you should see it. And so remember the one I showed you at the augmentation level where you had the M bound to the circle. The task, the aim is to conjecture the same property of the right angle inscribed in a circle, but in a different way. Here, the student is asked to find a position of the point M outside the disk, such that the angle A and B is obtuse. So the student is supposed to search for such a position, and so he or she will drag M all over the screen and to observe that the angle is still acute. So the idea might come, what if I drag the point M inside the disk? And so here the student can observe that definitely when M is inside the disk, the angle is obtuse. And so the property of the right angle triangle might come from the principle of continuity, that inside it is obtuse, but outside it is acute. So on the border, it should somehow be a right angle. So here in this kind of task, dynamic geometry supports exploring the geometric situation. It allows the student to think about what happens when I place the point somewhere else. And so P, in his article, said that this what-if property enabled by the software, by dynamic geometry in our case, is a creative means for generating and testing various scenarios for what could be given different hypothetical conditions. So this might also help distinguishing between hypothesis and conclusion, because the hypothesis what if I place the point M somewhere else, This is a condition, and what the observation is a conclusion. So these are very valuable tasks which are not very often used by teachers in their practices. So I will perhaps skip this example, because it is again an example at the modification level, because I see that time is running, and so I will go directly to the redefinition task. One of those tasks is to find the relation between objects. So here is an example. So you should now see this very simple figure in which you see 4 points. One of them is different. This one cannot be moved because it is constructed based on the 3 other points. And actually, the task for the student is to find a way how to construct this black point given the 3 other points. And so the student is expected to move around these points and to figure out the relationships between the points and to conjecture the hidden properties. So you can perhaps see that this point, this 4th point, is the 4th vertex of a parallelogram defined by the 3 other points. So this redefinition, here the dragging, the artifact dragging, supports experimenting on the drawing, helps students conjecturing hidden geometric properties, help testing conjectures. So it supports problem solving and inquiry-based tasks. So I will conclude by a brief summary of this panorama of different types of using dynamic geometry. So first of all, at the first 2 SA levels, we can see that the cognitive activity of the student is basically observing on the robust figure what remains unchanged. These tasks are suitable for teacher-centered pedagogical approach, because teachers can prepare these robust figures and just project these figures and let students observe and conjecture geometric properties. The drag modes here allows to discern these properties but while observing what varies and what remains unchanged, and very often in the tasks the points to drag are indicated, so the student is quite guided toward the points to be dragged. The underlined paradigm is robust construction, and a consequence of this is that the passage to proof seems very delicate because the visual conviction about the validity of properties is very strong. So the students very rarely see the interest and the need to prove the properties that are so strongly visually presented. On the other hand, the top levels, MR, support cognitive activities of inquiry, exploration, problem solving. They are more adapted to student-centered pedagogical approach, and the drag mode does not need to be prompted because it is a part of problem-solving strategy. The choice of points to drag is under the student's responsibility. The underlying paradigms are both robust and soft constructions, and what is interesting that the proof remains very meaningful because the properties are rarely visible, are almost never visible. They are only conjectured, so the need for a proof remains. And so I will conclude just by telling that technology itself is not transformative. It is the way how it is used that can be transformative. The model, SAMR model, allows to think about various uses of technology, and it is, to my sense, a tool of thinking about the consequences of these different uses of technology, whether they are student-centered or not, whether they engage the students to some cognitive activity, and whether they are more or less transformative. There are definitely instrumental issues behind these different uses because the students need to develop very particular instruments from these artifacts that are offered by these digital tools. And so we know that these are lengthy processes, and the teachers have a role in accompanying the students' instrumental genesis. So for students, there is a big challenge in constructing double instrument, not only mathematical instrument, but also didactical instrument. So this is what I wanted to share with you. Thank you very much for your patience and for your attention.